Welcome back. So now we start part one of this series, which is geostatic stresses. So let's get down to it, not waste any time. Um, okay. So let's assume now. So let's just do geostatic part. So the word explains itself. So geo means soil, and static. So soil under static conditions. So now let's assume we've got um, just slide down. We've got layered soil stratigraphy. We've got 3 layers and 3 different soil materials. So we've got gravel, we've got sand, and we've got clay. Now let's assume each one of these materials has a certain thickness. So this will be Z1, this will be Z2, this will be Z3. And each material would have its own unit weight. So this would be gamma gravel, gamma sand, and gamma clay. Okay. Now the question goes like that. So it says we've got a point of interest, say x, at a certain depth within the clay layer. Usually it's the midpoint of the clay layer. So Z3/2. And we would call this the point of interest or the point of investigation. Point of investigation. Okay. So the question goes like this. What is the stress at the point of interest? Now here by stress I mean sigma v and sigma h components. Okay. Now to first get into this topic, let's assume we have a completely dry, okay, and put this in capital to emphasize, completely dry soil. Absolutely no water. Water is the enemy. We hate it because it makes everything so complicated. Okay. Now what is stress? So before I get into stress, we know that the unit weight is kilonewton per meter cube. So that says the value of the unit force, the weight of the material per unit volume, okay, is that much. So the weight of the material per unit volume is that much, and that is a force. In the same time, the stress is kilonewton per meter squared. Okay, so it's the force per unit area. So the difference between a unit volume and a unit area is one dimension, which in our case is the height, z. Okay, so I could say that sigma equal gamma times z. That will leave me with kilonewton per meter squared. There is a very easy way to visualize how this formula came to be and what is the stress. Okay, so if you want to find the stress, we need to just multiply the unit weight of any material by the height. So if I'm looking at point x, so if I want to find the vertical stress at point x, I need to add all the unit weights of each layer by each layer's thickness. So that would be gamma times z for gravel plus gamma times z for sand plus gamma times z on 2 because it's midpoint of the clay layer of the clay layer. Okay. So that is the case of a dry material, completely dry. Now if I want to get the horizontal stress, because soil is anisotropic in terms of stresses and loading, the horizontal stress is not equal to the vertical stress. Okay, that's a fact. So how do you find the horizontal stress? Now we have a coefficient, so sigma h equal k naught sigma v, and k naught is the coefficient of lateral earth pressure, and usually k naught is less than 1. Okay, now we can visualize that the vertical stress in dry soils, I cannot emphasize this enough, in dry soils is the stress in the soil itself. Nothing else is sharing the stress with it. It's just the soil loading itself and carrying the stress. Okay, now that is the case of dry soil. Let's now talk about wet soils with water. So now it gets a lot more complex than before. Let's see how. So now, if we look at soils, okay, it's composed of solid particles of solids, soil, sharing the space with water. So water is filling the voids between these solid particles. And there is no air because in soil behavior, we only deal with soil that is saturated. Okay, so always the volume of air will be 0. Now, if we load this, the stress will be shared between the soil and the water. The same way, if we go back to mechanics of solids and we try to visualize our problem, if we have a block of concrete and we load this block with a force P, we expect that the concrete would react back with a force P concrete that is equal to P. Okay, so the concrete takes the whole force, and that is the case of dry soil. That is similar to dry soil. One material taking the whole load. Now, if we have reinforced concrete, again, this is the cross section, and we have reinforcement inside, steel. Okay, and we apply load P. Now we expect the reaction to be two components. Okay, P steel and P concrete, where P steel plus P concrete will be equal to P. So this is the behavior of a composite material. Now wet soil is not different, it's the same. We have solids and we have water, so we have two materials. So now if I apply this stress on this material, let's see what happens. Okay, I've got the solids and I've got water. If we apply load P, now let's say it's not a force, it's a stress. So if we apply the vertical stress, okay, the soil would react in sigma dash V and U, where sigma dash V is nothing but the effective stress. The effective stress, and that is the stress that your actual solid particles would feel. That is the effective stress, and U is the pore water pressure. Which is the stress developed in water due to the loading. Developed in water due to loading. Okay, so now we could say that, oh look, that the total stress sigma V is the components sigma V dash plus U, which is the stress in soil plus the stress in water. So soil plus water. Okay. Now we learned how to find sigma V. It's exactly the same as the case of dry soils. So sigma V, the total stress, is just the summation of the unit weight times the thickness of each layer. Now U is the unit weight of water times the height of water above the point of interest. Now let's look at some examples. So let's see example 1. In example 1, I'll try to draw a perfect rectangle. Nope. Okay, awesome. So in example 1, we have soil, let's say sand, okay, and we have this sand is perfectly saturated. So the water table is right above the sand. So the symbol of water table is this small rectangle. That is the symbol of the water table. That means the entire sand is saturated. Now we're looking at the point of interest, X. Try to fix that. Yeah, point of interest, X at a depth Z. And we agreed this is saturated soil. Now what is the total vertical stress and the total horizontal stress? Now we've done that for dry soil. Let's see how we would do that for wet soils. So sigma V, the total stress, is going to hold the same formula. It's going to be gamma sand times Z. Okay. Now, gamma sand is obviously saturated formula. If you remember, the saturated unit weight is GS plus E on 1 plus E times gamma water. Step number 2. Step number 2 is finding the pore water pressure, U, which is the unit weight of water times the Z water, which is the height of water above the point of interest. So if the water table is right here, the point of interest is right here, so Z is the height of water above the point of interest. It's going to be gamma water times Z. Step 3, I want the effective vertical stress, which is total stress minus the pore water pressure, which is gamma sand times Z minus gamma water Z. Step 4, I want to find the horizontal stress. So I find the effective horizontal stress equal to K naught times sigma V dash. Step 5, the total horizontal stress equal to sigma H dash plus U. Okay, now why didn't I just simplify this and say, oh, we can do something like that sigma H equal K naught sigma V, yeah, like we did before. No, this is wrong. Okay, for wet soils this is wrong. Why? Because K naught is solely defined as the ratio between sigma H dash on sigma V dash, which is not equal to the ratio of sigma H on sigma V. It's not equal. In case of dry soils, there is no water, so in dry conditions, sigma V is sigma V dash, and sigma H is sigma H dash. So I could say, yes, sigma H equal K naught sigma V. It's the same as saying sigma H dash equal K naught sigma V dash. Really, there's no difference. But in wet soils, yes, there is a difference. So I must get sigma H dash equal to K naught sigma V dash. And if I want the total horizontal stress, I must say it's equal to the effective horizontal stress plus the pore water pressure. Okay, so we have 5 steps. Now these steps are the script to solving the question. Okay, again, we must find the total vertical stress, which is the sum of gammas times the depth or thickness of each layer. We must find the pore water pressure, which is the unit weight times the total depth of water. Okay, this is the total depth of water. Of water until we reach the point of interest. Then we find the effective vertical stress, which is sigma v, total vertical stress, minus the pore water pressure. Then the effective horizontal stress, which is K naught times the effective vertical stress. Then we have the total, which is finding what we need. Total horizontal stress equal to effective plus the pore water pressure. Okay, and that concludes the first part of geostatic pressures. Thank you.